Hey, hi everybody. May I ask to turn on your camera, please? Thanks. Okay, let's start. Today, the plan is to somehow have a closer look at multi-cycle microarchitecture, which is an improvement over single-cycle microarchitecture. So we have discussed extensively about performance, and somehow you have clear vision why we need multi-cycle microarchitecture. Now we are going to have a closer look how it looks like. Before we jump in, do you have any question for me? Anything that you want to bring up? I presume you saw my message earlier about the next homework. So make sure that you also look at it and submit it on time. And next week we have midterm. So make sure you study the material and you understand everything. Hopefully it should be very easy for you.
I have a question.
Yeah, go ahead.
Is there going to be like a practice exam or a study guide for the midterm?
Presume not. I don't think that I find any time next week to do it. If I find any time, I will definitely do it. But like few suggestions, like make sure you review the lecture slides, and some of the lectures, the videos are available, right? You can review it, and also the homework, quizzes, stuff, and also hopefully I strongly suggest look at these two important chapters relevant to this course that we have discussed, right? So chapter 6 about programming, right? MIPS assembly, and chapter 7 about microarchitecture. Yes, Ross.
I mean, I understand if like you might not have time, but I don't know if you could like maybe get in touch with Norris and see if he maybe could do if not a study guide or a test, like a practice exam, maybe just a review session, maybe like an hour-long review session, something like that. I think any sort of prep like would be good, and I would definitely go to that. Obviously, like we've had issues with like time in the past, but like that's just a thought I had.
Yeah, sure. I will definitely discuss it with him today. Hopefully, he found the time. I will ask him to send out some possible slots, and you select and see which one is most suitable for you guys. Yeah, that's actually a good idea. Yeah, it doesn't need me, and like I think it's better not me having this. You hear from somebody else's, right? So that would be good. Yeah, sure. Okay, great. So if you're interested about knowing more detail about specifically multi-cycle microarchitecture, this seminal paper, the best way to design an automatic calculating machine, is mainly describing the key ideas behind multi-cycle microarchitecture. But again, it's optional, up to you. And the key ideas are few, right? Instead of having one cycle in order to transition the architectural state, we could have a finite state machine that this finite state machine sequences between several states. And these states are actually defined by the control instruction, right? The control signals. So transitioning between different states is one of the key ideas which enable us to realize multi-cycle, and you will see how it looks like, what a state mean when you see an example. Hopefully you are familiar with finite state machine, but the definition of finite state machine is very straightforward, simple. FSM is a model, mathematical model, consists of multiple different states and transition between the states, simple as that. But you will see an example. Okay, and the state is defined by the control signal, which are specified in this state, and you will see example what exactly how an state looks like. And control signals for the next state are uniquely, and it is important, are uniquely determined in the current state. Whatever you see in this current state determine the next, essentially, the control signal for the next state of the machine. You already know about this instruction processing cycle. Like there are different stages from fetch, decoding, evaluate address, fetch operands, execute, and store results. And you saw that all of these stages happen in one cycle, in single cycle microarchitecture. Here, you can think about this as now the states, like instead of like having one state or only one transition like between all of these stages, each of these stages could consist of multiple different states, depending, or in a way, like each with this realization of multi-cycle, you could imagine that we are able to carefully assign or design the machine in a way that assign different cycles, number of cycles for these stages, right? Say like fetch, maybe 2 cycles is enough, right? And say for decoding, since we need to like access to the memory, maybe you need to spend more cycles, right? And also in store results, again, sometimes you store the result into memory, depending on instructions. Sometimes you store the result into register, into the register file, and then you may want to have the flexibility to have different number of cycles associated to this stage, right? So you get as a result more flexibility for each of these stages, and that's why you can design the machine to basically give enough resources differently. And by resources here we mean like the amount of time that you make available for each instruction, depending on how much they need it, right? So in single cycle, you saw clearly that like the instruction which were very efficient, like they got tons of time, which they didn't need really. And during that time, the machine were not used, so the utilization was very low. Now you are able to give each of these enough time, so those who need longer, yeah, they can use it. Those who do not, like much shorter. So you have this flexibility of assigning appropriate resources depending on the demand of each instruction. Okay. So instruction processing cycle are now divided into states, multiple different states, and a stage in the instruction process cycle can take multiple states, right? So that's the relationship between like the states and a stage of the instruction processing that you are aware of. And a multi-cycle microarchitecture sequences from a state to a state to process an instruction. And this sequencing of states throughout this finite state machine, which is a well-defined model, determine the behavior of the machine in that particular state, right? Which are specified by the control signal in that state, right? So, you can imagine that we have a finite state machine transition between different states, and different components in the microarchitecture, in the hardware, will be activated or can be used, and the data could be processed throughout and be available for the next states where the machine goes through. Yes, Ross.
So is this like the same thing as like the Mealy and Moore models that we dealt with in 211? If I remember, those were state machine, like we were dealing with state machines, if you know what I'm talking about. Is that pretty much the same thing? We just haven't really visualized it?
Exactly.
Okay,
it's pretty much the same thing. Yeah, and you will see shortly example, so you can correspond it. And like if any part is not matched based on what you remember, yeah, we can discuss it. That would be good. So for those who forgot what is a finite state machine. And the behavior of the entire processor is specified fully by this finite state machine. So you can imagine that this finite state machine is the key, is the main controller, right? So is the orchestrator of the machine. And this is important. And also, again, I would like to emphasize, please think throughout this lecture and try to make a sense of what we are discussing. And if any part is not clear, stop me and ask me for explanation, because I would like you to understand it very well. So in a state or a clock cycle, so now each state, you can correspond it to one clock cycle. So these states are like short, because this is what we wanted to achieve, right? Having a short clock cycle, very fast, right? So we are able to process instruction very fast. So control signal control two things, okay? That's very important. How the data path should process the data, similarly to single cycle, with like you will see example how different it is, and this difference is really minor, is not major. The key skeleton of the microarchitecture would stay similar with like few changes here and there. And how to generate the control signal for the next clock cycle. So these two, right? So these two are the things that control signal controls, or make sure the machine will transition to. And this is, if you think like this is the key task of orchestrator, right? And here is one example that you remember, right, from single cycle machine. And like when we go to the example for multi-cycle, it would be good to make a correspondence, right? So always, since now you have a good understanding of this single cycle, always try to make the correspondence between this and multi-cycle to understand it very well. And these differences are minor in some sense, so it's easy to catch it. And in single cycle microarchitecture, you remember the cycle time were limited by longest instruction. We have discussed this many times, so I'm not going to discuss it further. And we had like some repetition of hardware, right? So we have a bunch of adders, like remember here, like we had like some adders, like here, for example, for incrementing PC, and here, right, and here. So all of these arithmetic operations, or here, this shifting, could be done in ALU because ALU currently have the capability to add or other functionality. So we had a bunch of additional resources here which were not really necessary. This could be done through ALU. Also, like weirdly, we had separate two parts of memory separated, like for instruction memory and data memory, because like it was not possible otherwise. We wanted to have one cycle for everything, and like we needed the instruction memory in here in order to first retrieve the instruction that needs to be executed, and there we needed data memory separately. But in multi-cycle, we are not going to have this repetition. Like we use ALU for all arithmetic operation, including incrementing PC. And also you will see that we are able to have higher clock frequency or shorter clock cycle, right? So these two are the same. Simpler instruction obviously run faster. They don't need to wait. And as a result, the cost of or overhead of hardware will be reduced, right? But in addition, you will see that we need some additional pieces, mainly in terms of flip-flop, mainly in terms of some components like registers that we need in order to store intermediate results. And to remind you, if you remember, so let me explain this for you to get the idea. So you remember that we had architecture state, and we had architecture state prime, okay? And we wanted to have this property that no matter what, the programmer from the external, above the instruction set architecture, because like this is what programmer assume, right? So the programmer assume that like after executing one instruction, it sees different state, right? But during the execution of instruction, the architecture state should not change, right? So this is the architecture state before execution of a particular instruction, and this is after execution. Okay, in single cycle, it is, and this is like, it is like an important thing. This is what we really want to preserve, right? So like there is no messing around this property, would otherwise things could go wrong massively, and that's a key property. Okay, but like preserving a property at a layer is something below this layer. We could do anything as long as we could hide things, right? And like this happens in real life, right? So maybe like you're assigned a task and you're supposed to like preserve a certain property, right? So as long as like the layers above you do not see these changes, right, what you do in order to solve this task, that's fine, right? But you should be able to guarantee this property that in between, it shouldn't be like, for example, that's a bad example, but like imagine that I give you an assignment, said like no looking at the book, for example, right? So as long as I don't see it, you're fine, right? So that property is preserved, right? But if I see it, if I be able to see it that you are using the book, you're in trouble, right? This is happening the same, right? So we have a layered architecture, like programmers should not be seeing any changes during the execution of instruction, but layers below we could like do everything we want as long as we could preserve this. In single cycle, it's easy because like really there is no change in architecture state. And again, for those who forgot, architecture state is nothing but the memory, right? So what you see in the memory, what you see in the program counter, and also what you see in the register files, right? So these are the architecture states. So if like in the middle of execution of instruction, you write to a you write to a register, then you violated the this property. Okay. So in single cycle, you're sure that this would not happen because like this is in single cycle, this is cycle like n. This thing will appear in cycle n plus 1. Okay. This is by definition of what we have in single cycle microarchitecture. Okay, but in multi-cycle, the system could transition to multiple hidden states. Okay, so this could be like AS plus like maybe alpha 1 AS plus alpha 2. This is like the things that we change, but the programmer still different cycles. Like this is like cycle this is cycle n, right? So this is cycle n plus 1. This is cycle n plus 2, right? So again, like programmer cycle n plus 1, see the same, right? Nothing has changed. Then you will go all the way, and at the end you have AS prime, right? In like say cycle n plus m. Okay, some cycles later on, this transition to a new state will happen, but in the middle there was no changes in the architectural state. And like during these multiple cycles, like one instruction, for example, were executed, okay? So this M could vary here, like what instruction it is, right? So if instruction like require lower number of cycles, like M is smaller. If instruction is higher, obviously M is larger. So at some point in this architecture state, new architecture state will appear once like everything regarding the execution of that particular instruction has finished. Okay, is this clear for you? Because this is fundamental property that you should know. And then going back to the slides. Okay. So what do we want to optimize here, right? We want to obviously have a single memory, right? That's one thing. Like we don't want to separate instruction and data memory. And as I mentioned, we want to like reuse resources instead of like repeating them for different purposes. So we want to reuse things and increase the utilization of these resources for the machine, for different instruction. Okay. So now let's start a particular example to make a sense how it looks like. We start by load word. And you remember load word, we have a register here, T0, and we have an address, a base address plus an offset. So we want to read the instruction from the memory, that's the fetching, and then read T1, this is the base address from register array, and then add the immediate value, like 20 in hex, to calculate the memory address. Okay, now we have the memory address, we want to retrieve the content. Read the content of this address and write it back to register T0. This is the semantic of this load word that you're aware of, okay? So this semantic is well defined, very clear. And now we want to implement it. And again, remind you, like, think about like differences between this example and what you have seen in single cycle, okay? And think about like things that I just have discussed about this architecture transitioning, because I'm going to ask you a question. First, step one, we fetch the instruction. We access the memory, and memory now in this case, like one memory, both instruction and data. Okay, so reusing of the memory, one component less. So we send the PC, we ask for the instruction, okay? And then here you see a new thing. This thing is, you can think about it as a register. Registers are implemented by flip-flop, right? So these are logics, digital logics that enable you to store data, right? So you store what data? The instruction here, right? So you store whatever you get from the memory into this register, and that's step one, okay? In one cycle, for example, say. So by the end of this cycle, like you have some data in register, okay? So like that's good. Then next step. In the next step, what we want to do is to access register file, okay? What register file? We need to have the encoding of the instruction, and we have the encoding, right? So we know like what bit number we should send it to find the right register for us, and then in this case, the register that we want is the register that has the base address, right? So the base address for retrieving the address of the memory we want to retrieve the data. And we put the content of this, in this case, if you remember, it was T1, right? So we put the content of T1 again to a very similar flip-flop or register, right? So you already see that, like, did we have these registers before in single cycle? Or
No.
these are new things?
No.
Why we didn't need these registers before? Can you think about, or can you guess any reason why we didn't need it?
Well, if we might need different registers for writing and reading, because if we can do things like in parallel and multi-cycle, like we could use multiple registers to do multiple things at the same time, perhaps.
Yes, but I'm asking about single cycle here, right? So I mean, like the idea of multi-cycle was to use less resources or like reuse things. So two questions. First of all, why we need these new guys here? Okay. And if I'm saying these are like registers, why the heck we are not using the register file here? Why we are not using the register file if we were supposed to reuse things? Because we could reuse things we could put things in the register file after we retrieve the retrieve this in from the memory, right? So I want answer for these two. think about it. I'm explaining the next few part until we finish the whole things, but think about it as I'm explaining. This is very important, okay? So now we access the register file, we put the content into this flip-flop, right? And then we also need to sign extend the immediate, right? So because we had this offset, right? And then once we do this, we want to add this together, right? We want to add base address, which were located in T1 register, and after sign extending the immediate offset part, we want to add them together. This is like, it was specified by the semantic of load word, right? So you already know that as a part of the definition of this particular instruction, right? So after you add them up, after you add the base register with the offset, you again send the result, put the result, store the result into a different new guy, different flip-flop, right? This is what, and the content of this is the exact address that you need to refer to in the memory, and this is what it happens in this stage, right? Or in this state more clearly, in order to retrieve what content is stored in the memory in that particular address. So you need to have access to the memory again, and again, to repeat this memory, same memory. Now we need data, access different part of the memory, but this memory is not repeated twice, right? So it's one component. So as a result, you already know how to manage this, right? So you need to add this component, this mux, in order to be able to select, because sometimes you want to retrieve instruction, sometimes you want to retrieve data. And you already know that when you want to increase reusability, when you want to access to one component with multiple different situation, you need to have muxes, right? So we already discussed that. That's one of the strategies that you already know. And then you have a signal there to control, like, now we want to increment PC, or now we want to, access the data memory. Okay, and then store the whatever you retrieve here to a new guy again, right? This new flip-flop. And then next, you know what to do, is the next stage, next state, that you need to write to the register file whatever you have retrieved from that memory address. Okay, and in addition to this, you also you already know that you need to increment the PC, and like, because like you always need to increment the PC. Okay, that's simple as that. This is the whole things that happens in multi-cycle microarchitecture for assuming only load word, right? We will add few more components or data paths specifically when we discuss other instructions. Now this is good enough for executing multi-cycle version of load word. Back to my question. Why the heck we need these new guys? Why the heck we need this memory, these registers as a flip-flop, considering the situation that I just mentioned that like in multi-cycle, one of the goals is to save hardware. We wanted to reuse hardware. And like we already know that like we have register file, why we did not reuse the register file there? Why we didn't do this crazy thing? I'm waiting for you to answer.
I mean, I'll take another stab at it, you know,
Sure. Yeah.
quiet room. But I mean, at least what I remember from like the flip-flops, like, you know, when a bit would change, you know, from 0 to 1, you'd want to change, like that could affect like several different components. So like if the flip-flop changes bits, like these flip-flops, what they need access to. So if a bit, like if we go from active, like from low to high or high to low, like 1 to 0, 0 to 1, you need access to change all those things like concurrently, if I remember correctly. That's kind of another like thought I had.
So, I mean, like, but how this answer my question? Like, for example, say like, why we didn't have these hardware components in single cycle? Why? And why we have it in multi-cycle?
Is it because that when we're working in multi-cycle, part of the purpose is to reduce the number of components compared to single cycle, and so as a result, we might need to add some smaller, more efficient, faster components to make up for it?
Yes, but in this case, so you're talking about the trade-off, right? So
Right.
say here, but wait, like, did I say that these flip-flop are the same as registers? Like registers are implemented like with flip-flops, right? Registers are nothing more than that. Like, why we didn't use that if they are the same? Like here, like one idea could be like, say, hey, like here we need like one register, right? But I would say, okay, like you have like 32 registers there, use those. Why you are not using those? They are the same. That's crazy if you want to like add new hardware. Like we are not spending more money, adding more hardware. Why? Is a fancy thing, or we want to make it complicated for getting more money? Why we are doing this?
Is it so? Are we just doing it to simplify it? I mean, if we have those registers available with those flip-flops, we can just use those as well.
So your suggestion is that probably is not a good thing. So we should reuse the register file here.
That's kind of what I'm thinking at this point.
Okay. I would like to hear from others. Bella, do you have any opinion here? I cannot hear you.
Sorry, I don't really have an opinion here. I was just a little lost and I was going to rewatch the lecture later, which I normally do and catch up with it.
So, sorry, I didn't hear it well. You said that you do not have any idea?
I don't.
Okay, that's fine. Let me call others. Colin, can you hear me? Do you have any idea here?
I mean, it just doesn't really make sense to me, because if we have those registers that we can use, I don't understand why we are doing this process with what you showed us. So I'm not really understanding how or like why it's like that.
So you basically are in the same line as Noah mentioned, right? So
yeah, as Noah, yeah.
You should have used the register file if that.
Yes, correct.
Right? Okay, that's fine.
I have an idea.
Yeah, go ahead.
So are the smaller registers used alongside the larger ones for like preparing the next instruction? Like storing like a parallel sort of process maybe?
Mm-hmm.
So that while you're focusing on whatever's being like crunched at first, the like the ones alongside that are smaller are being used to like get the next one in line, possibly.
Yeah, you are getting there. You are getting there. That could be a reason, but can you elaborate more? Or maybe others can elaborate more now that you hear something new, some new thoughts here. Let me see who we have in the class. Miles, do you want to add something? Miles, can you hear me?
Can you actually repeat what he said again? Or like whoever said that, can you repeat?
Yeah, Bobby was saying that maybe we need to have some coordination in between, because like we have like different stages, and maybe we want something in the middle, right, to coordinate things. I guess that is what you said, Bobby, somehow, right?
Yeah, like something along the main process that is preparing like what comes in line next, like an assist kind of.
Imagine like, for example, say like we are doing this, what's the English name for this running and multiple people, they give the things to the next one to go next in Olympics. You see, I forgot the name of this.
Relay?
Yeah, so you give this thing to the next person, would otherwise cannot proceed next, right? This thing, stick, is used for coordination, right? Because next person cannot start running unless he or she has that, right? So that's a way for coordinating things when there would be a need for coordination. This is, I guess, what a close example of what Bobby said. I would like to hear other thoughts as well. Do we have any volunteer? Corey, do you want to say something here? I'm not letting you to get away with this. I would ask all of you. Charlie, do you have something to say? Please enable your mic so you can speak. Patrick, can you hear me? Can you say, do you have something to say? Are you guys listening? Apparently some students are not listening at all. Ross, thanks for joining. Do you have something to say?
Hey, sorry, Professor, but no, I'm struggling to understand the material.
Okay, that's fine.
I think it might be time to maybe dish out the answer. Maybe.
You said what? You have something?
I said I think it might be time to dish out the answer.
No, I insist on this. I want you to, because that's very important. Would otherwise like it's better to like wait until you get it right. Honestly, it's very simple, and I just explain it honestly. if you would have followed what I was saying. It's just, I just explained it like a few minutes ago. Matthew?
Does it have anything to do with pipelining?
It is related to pipelining, but since we have not discussed it, no, I don't expect you to explain in terms of pipelining, right?
Is it about those hidden cycles at all? Like you said, like when we go from AS to AS prime, like AS to AS prime,
might be.
that's what we see. But you know, like this type of architecture might allow us to have those hidden cycles going on in the background before we necessarily reach AS prime, and maybe on our main interface. So
how,
like, you know,
how? Reason more concretely. You are getting there.
Well, I mean, if we have several flip-flops, that could allow us to, like, that's what I was kind of trying to say before, but it was less formed because I wasn't thinking about the architectural state, I guess. But if we have several flip-flops, like that allows us to, like, I guess, like the flip-flops will give out other signals to flip-flops, and then that'll change, I guess, the bit from like 0 to 1. And so we could, I don't know, I'm trying to piece together like on the fly here, but you know.
No, you're getting it.
Yeah, I could just maybe, I don't know, somebody can maybe take the torch, but that's kind of, that was kind of my idea. It's like, you know, we have those hidden cycles that you were saying, AS plus alpha sub 1, AS plus alpha sub 2, you know.
Yeah, but why that has happened, might have happened, right? If that's the idea, why that might have happened with this, but, and like contrasted with single cycle, and why we definitely need this newer stuff in order to preserve that property, if this is what you wanted to say. So basically what you are saying is that adding this stuff is a way for preserving that property, but can you add more why?
Well, we have, I guess, like predefined paths through a single cycle like microarchitecture, that's AS to AS prime. And we're doing like the instruction, we're completing the instruction in that cycle. And we have those direct paths rather than like, we don't have any flip-flops there. So there's no, you know, there's no switching the control based on the bit, I guess. Like it's just one straightforward path, and we're taking one path through. And that's not activating anything else. It's like a linear path, if you will, I guess, as opposed to this, which might not necessarily be the case because flip-flops are giving output signals to other things, and we have like multiple flip-flops.
Could we, let me also ask this, could we add these new guys in single cycle too? Could we add those? What do you say to have there? Like, couldn't we like add these flip-flops in single cycle too? Things will go wrong or not?
I don't think you are able to add them in single cycle because single cycle depends on everything having constant control signal outputs. It depends on all the parts being synchronized during that one cycle and then resetting after it. So if we start playing with the cycles in single cycle architecture, it won't work. It'll malfunction.
Yeah, but like, couldn't we add like, say, hey, let me, so for example, let's go back to this single cycle guy. This was our single cycle, right? Couldn't we add, say, here, like a flip-flop? Like we had a bunch of stuff, right? We had like, even we have an additional adder. Like we added some crazy nonsense hardware stuff there while we had them somewhere else. But like flip-flop is simple, right? We could like randomly add in between, right? What could go wrong, right? In this line, we cut it and we put a flip-flop. Like we ask the guy, hey, like, would you please store like whatever I have in instruction memory, like there, and then later on pass it over next.
Well, does it concern the fact that like we're trying to deal with the data in the instructions in the same like all in one rather than like what you were saying, separating data and instructions.
Yeah, exactly. Like, because like in single cycle, we wanted to make sure that like all of these things will end by the end of this single cycle, right? On the positive clock side, right? Like adding this, like, okay, if you ensure that like you do all of this transition from memory, instruction memory to this flip-flop and this flip-flop to register file in this cycle, then it should be fine, right? Or still you believe that it's not fine? And if it's not fine, why? Why is not fine? Or more specifically, could things go wrong, or maybe what consequences it has?
Is it like what we're trying to control? We're trying to do two things with the control signal, and which I believe that's not what we're trying to do in single cycle. But like that's what, like with multi-cycle, we're trying to like process the data and prepare the next instruction at the same time in one control signal.
That's right. That's absolutely correct fact, but has nothing to do with this question.
I mean, I'm trying every avenue at this point to see if I can.
No, thanks. Yeah, this is very good. Like this is what I wanted to hear. Others, please.
Is there any way you could just real quickly just run through the question one more time? Because I think I'm getting most of it. I don't think I have every part of it correct.
Okay, let me explain the question more clearly, right? So single cycle, like we had a bunch of stuff we added, right? And then in multi-cycle, we claim that, hey, like one of the things, and I have it in the slide, right? So we want to take out unnecessary stuff, right? So yeah, we remove this data memory. We make the data and instruction memory the same one component, so that's good thing. And later on, we have this ALU both for sign extending things. Previously, we had one adder for doing this, right? We were not able to reuse ALU. And then like also for basically incrementing PC, we also, you see here, like we use again ALU, right? What we added here, like we add one new guy here, somehow we had this mux here, but we add one new element, and we added 4 here, right? Because we need to increment PC by 4, right? So we reuse ALU for incrementing PC, right? So we reuse this stuff, right? But what I'm asking is that few questions, all of them are relevant. All of them are relevant and pointing to the same fact. We added new flip-flop here. Okay, this guy, right? Which were not there before, like this guy, right? We didn't have this flip-flop before in single cycle. And somehow this contradict with the key design principle of multi-cycle, that we wanted to save hardware, we wanted to reuse things, we wanted to like make things simpler, we wanted to like make the cost lower, but we added new hardware. Why we added, right? Why we added this new hardware? And like I gave an example that these are the same as a register, what you have as a register. So these are like the same hardware, similar hardware in terms of design as a register file, right? Register file, we build them through flip-flop, right? The same thing in terms of hardware, like why we could not reuse register file, and to contrast with the single cycle, like why we didn't see this, why we didn't like use this hardware in there as well, like why we didn't have these in single cycle. All of these 3-4 questions are saying the same thing, referring to the same fact.
Okay.
I want the same one reason for all of this.
I think I've got it now. I think I've got it.
Okay.
So we added that flip-flop, which is contrary to us trying to eliminate everything, because at this point, now that we're in multi-cycle architecture, we need some way of telling the program or telling the hardware that we're not too busy with one operation. So that flip-flop is in there to store that data until we're ready to use it again, right?
Okay.
So we run through the first part with the instruction, and then after that leaves the ALU, then we increment the process counter during the second part while that's doing whatever else operation it needs. So that flip-flop is there just to kind of provide us with a bit of lag behind so that it works out.
But why we didn't have this like in single cycle?
In single cycle, we didn't need it because we had our own separate set of hardware in order to take into account those tasks. We had these separate ALUs and separate memory read and write for just so that.
Or let me ask, what would go wrong if we store this in register file?
If we stored them in a register file, there's a chance that we would accidentally overwrite that register file and lose the data we were working with.
Wait a minute, didn't we did the same thing in single cycle? We did the same thing. We stored this in like in register file directly. Like why like things didn't go wrong here, but could go wrong there?
And that's because we're working with multiple sets of data at once, because as we have one process finishing, another process is beginning.
No, I'm not talking about like multiple, like we are not like executing things in parallel. Like imagine that like one, like there's no parallelism for now. Like imagine one instruction. We're now talking about load work. And like there's no parallelism. Imagine that there's no parallelism. Like if we are like running one instruction at a time and there's no other parallel things going on, like why we want to, why we couldn't reuse the register file?
Can I just say what I think on this? It may not be right, but I think I got something.
Yeah, absolutely.
Okay. So from what I realized, the single cycle that goes for all the instructions, so we don't need the multiplexer because it runs at once.
Okay.
But for the multi-cycle, we need it because we need something to direct which, with the clock cycle, which step of the instruction to operate. Otherwise, it wouldn't know how to save the time because it wouldn't have anything to direct it to the step of the instruction.
That's 100% correct. And what Noah said also 100% correct. What Ross said also is correct. All of these are correct. But let me elaborate on this. So you all got it right. Things that I wanted to hear more clearly is about this property that I mentioned, like transitioning between AS to AS prime, right? As Bella mentioned, in single cycle, we do not need it. Or more clearly, related to exact question I asked, we could add it and nothing could go wrong in terms of this property. Like nothing, we could technically add these components in between. We could add this flip-flop in between. Nothing will go wrong. But as Bella mentioned, like it adds to the like time that it takes to execute the instruction, right? Because writing to flip-flop takes time. It's not like zero time. It takes time. So we are adding some artificial time which are not really needed. So like we add directly to register file and like we are not violating the property by adding things to register file because programmers see the next state, see this change to the register file. Like she doesn't see the changes between the clock cycle in one clock cycle. Like after like clock has finished, she see that, yeah, like I saw that this register has changed. Even though like maybe we wrote to the register file like in the middle of the clock cycle, and really clearly we wrote to this register file in the middle, but like the effect will be observed by the programmer after like clock cycle has finished. And that's the property that we have. In multi-cycle, like listen very clearly, in multi-cycle, like we could not go away with that. We could not go away with this because why? It's simple, like very clearly. If we write to this register file, like imagine that I'm removing this, I'm writing to register file, think, each step, each state is one cycle. Like when the clock has finished, when we go to the next clock cycle, programmer will see that the register file has changed. And this property has been violated because register file is part of the architecture state. But this register, this new guy, did we say in the ISA, have we ever talked about this register in ISA? Like, did we were aware of this register when you are writing assembly, MIPS assembly? No, you never saw this register. You never saw this register when you did assembly. Like you had a bunch of like 32 registers. Like this is new. We didn't have this. We don't see it. The programmer doesn't see it. So we could add things as long as the programmer is not aware of it. The architecture state for her is the same. But if we write this, she sees this. This is part of the architecture state. This is part of the things that the programmer is aware of. So if we see it, yeah, obviously we could see it, but we will violate this property, right? Even though they are the same, but since this register file has been defined in the ISA, if we write to it in a cycle, while the instruction still is ongoing, here like instruction is still ongoing, it's not finished. It's not finished by any means, like we have other states, right? Will be finished like when we are done at the end, right? But in the middle, it's not finished. So if we like two things, we write things in the middle, like we will violate this property and things could go wrong. And that's why we need this in order to preserve this important property that we should really preserve in this multi-cycle. So that's important. Like, make sure. I don't want you to only, like, I could present this in a way that, like, yeah, giving you no reason, right? Like, you should accept it from me. Like, we need this hardware, but none of you asked, like, why, right? I hope now you have a clear, like, understanding of why, like, we needed this. This is the first principle in the multi-cycle design. Would otherwise was impossible, right? So that's the minimum thing that we could add. Yes, Ross.
So are we trying to utilize, like, you know, it obviously depends on, there's different types of flip-flops, but like, you know, toggle, set, reset, like, are we trying to set those sorts of things up while we're doing the instruction, basically?
What are we trying to what?
Like, you know, I'm talking like with flip-flops, like you have different options depending on the bits that are like whether you get a 0 or a 1, and it's like
Like, I mean, by flip-flop, you can think about this as a register. It's not 1 bit. It's like 32 bits. Like you should have enough storage here in this. Is an array of flip-flop, right? So you should have 32 bits here in order to store the instruction, right? So you have enough storage, it's not 0, 1.
Yeah, but it would be like analogous to like, you know, using like the set on like a flip-flop. You know what I'm saying? Because there's different functions for a flip-flop. That's what I'm saying. And
Yes.
like which one of those functions you're activating.
Yeah,
like-
yeah. Yes. So like here, each of these have their own control signal. Each flip-flop, they have its own control signal, right?
Mhm.
You see the clock, meaning that like by clock you should like store it, right? On the positive edge of the clock, right? So the right control signal will be sent to these flip-flops, right? I think you might be asking a different question that I don't get it, but let's discuss it at the end when we are done. So that's really what you need in load word, in a store word, right? So now things become clear, right? So let's reason what else we need, right? And this could be reason about the differences between different instruction. In a store word, what you need is to basically read from the register file, right? And then once you have this value, you want to store it in the memory. So you need some wiring here. So again, like you extend this flip-flop, again, like now accepting 2 inputs, then sometimes you want to store this second one, right? So after you read the content of the register, put it into this, and then you write it to the memory in the next clock cycle. So this is the only thing that that you need to add here. For other instruction, you need few more other things. They are minor, like for example in R-type, you need this new guy where you had this. Actually, these are the same muxes that you had in single cycle, right? So nothing has changed really from single cycle to multi-cycle. So we add this, and then here, like we add this new this stuff that were before actually in single cycle. The only thing that is changing here, I think we had this also in single cycle as well, right? So so the changes that you saw here, like we have now a new muxes here because like we make the data and instruction memory the same, so we needed to add this mux here with this new control signal, right? So it's instruction or register data. Sorry, instruction or data. What else? Yeah, and these flip-flops, right? So like it's not fancy, it's similar as single cycle, but now like you have a control unit that like transition between these different states and determine the control signal for the next cycle, right? So, and these control signals are the same. Like you have now like the only difference, as I said, like this instruction or data signal where you didn't have it before, but in terms of control signal, they're pretty much the same, right? Is there anything else that we didn't have before? I think that's it. Yeah, I thought probably there is one more thing, but anyway, like it's pretty much same, right? And you now have a clear vision why. Let's quickly discuss this, and then we are done. because I want you to see the states. So each state like is simple as that, right? So so this is the S0 state 0 fetch when we want to fetch, right? And you see, like we come from reset state to this new state S0, okay? And then we transition to S1, which is decoding. So you see the correspondence. So in the first state, we want to basically set I or D to 0. So this guy to 0. Why? Because we want to transition PC to the memory and all the way to this flip-flop. And we need to also write to this flip-flop. So, oh, the new signal is this IR write, right? So, because we didn't have them before. So we need to set this IR write to 1, right? That's what's happening in this state. The rest, what else? So we don't want to write to register. That's why it's 0. We also here we want to also like in this things, we also want to set this one to 0, 1, 0. And this is the code for addition. So this is used for incrementing PC, right? So this is what happens for incrementing PC, and also we want to set these to 1, right? And then next state, again, this is what happens. These you see this next state. We want to write from the instruction and basically do the stuff that we discussed, right? So retrieve the data from the register file in order to be written to the next one, and then the next cycle, the next state is 2, where we retrieve the memory address, right? So in this case, these are the control signal, right? And then this is the next state, right? So, and you see that like the finite state machine, you see clearly here that this is for load word, right? So it goes from different states, right? So here S1 was decoding, and then S2 was memory address, right? And it's decoding, and in memory address, you see the control signal that you need to set appropriately. So here also in memory address, you need to use ALU. So you need to use the right functionality for ALU up 0, 0, for example. And then memory read. So you need to set the control signal for memory read stuff, and memory write back. So so you need to set again the right control signal here. You see that memory to register is set to 1, meaning that you should be able to write to register, write back to the register. Okay. And here, like for a store word, right? So you see the transition, right? So in this case, in this is finite state machine, these states are for load word, if operation is load word, right? Here you see if the operation is a store word, right? So in finite state machine, like the transition to the next state is actually depends on whatever you have in this state, right? So in this state, it turns out, if it turns out to be the operation during decoding, you will see, right? So whether the operation is a stored word or load word. If it's a stored word, then you clearly would transition to a different state, right? Which is different from like load word, because in load word you need to do a slightly different thing than a stored word. And if it is R type, then you have different states, right? So you clearly need to send different signal for R type. So that's why you see different states. And also for BQ, you also need different, because you need to be able to branch to a new thing. And that's actually the complete multi-cycle controller that sequences between different states in order to generate the right control signal for the next step of the machine. And that's is precise. It's defined completely, and the machine knows what control signal needs to be generated at different state. And again, think about it. Think about single cycle. Why we didn't have finite state machine? Answer is simple, because we didn't need different control signal. We could generate the whole control signal for the whole machine, completely given for mostly given the opcode. Once we have the opcode, right? You remember the table, and sometimes we needed some signal during the data pass, which makes it a little bit more complicated, but we didn't need any states in order to make that happen. So that's a definition that we have, right? Let's stop here. There are a few more details, obviously, there are some immediate instruction. There are jump that will add some new states to this finite state machine, but somehow this is for all these R-type PQ load word and store word. This is all you need to know, be aware of. Hopefully, again, importantly for me is for you to understand the basic design principle, these fundamental principles, rather than detail about what, right? So I want you to understand, reason, analyze, make a sense, and create and innovate in the future, right? Otherwise, you cannot innovate, become the next big person by just memorizing things. Yes, Ross.
Well, I was going to ask next class if you could compare, if we did the same thing in multi-cycle as opposed to single cycle, but I just realized we'll kind of I don't that's the class. It's it's an entire week from now because of the wellness day. So I mean, but that's just an idea. I think it'd be super helpful if we could you could set up an example where we do the same exact thing through both, so we could really get an idea of what are we doing,
Yeah, absolutely. Yeah, we can review the single cycle again in contrast to multi-cycle and make a sense out of it. Sure, yeah, we might make it and we could do it. Yeah.
Okay, cool. Thank you.
I will stay for a few minutes here if somebody have any question.
Actually, there was something I wanted to ask really fast, but I think you mentioned it, that we'll talk about it next time, is the jump instructions. Because when you were mapping out the different types of instructions at the end, I noticed that we didn't talk about jump instructions yet.
Oh, in single cycle, you mean?
In in multi-cycle, because I know in single cycle we'd used a couple external components, and that's part of the reason we have that separate process counters to handle jump instructions. But in multi-cycle, we'd have to do that differently. We'd have to take into account the fact that we're using the ALU at other times as well.
Right. Yeah. I will discuss this.
Okay.
As well.
And would we kind of do that the same way we implemented the register from earlier, that example that we really couldn't get through for a while? We would do that kind of the same way, where we'd store a value and then wait for it to be free until we chuck it through.
Okay. So
like we would basically, what I'm asking is, would we wait, or actually that would be its own separate command, so we would know that the ALU would not be occupied at that time.
Oh yeah. Yes, because you are asking about the conflict between different states, that sometimes like how we make sure that like we are not requiring ALU at the same time for different functionalities, right?
Right.
Is this what you're asking? Yeah, that's happened throughout this definition of each state, and that's why we need that, right? Would otherwise, like with one state, we couldn't make it happen, because like sometimes we need ALU for like incrementing PC. Sometimes we need it for executing the semantic of the instruction, right? And like if we have one state, like you would never ever be able to do that. But with different states, we are making sure that like we would not need ALU for different purposes in one state, right? If we did that, we could make it like two different states, right? And that's how we can reason about it, right? Okay, in this state, like I'm thinking about like doing this. Is it possible? You reason and say that, okay, I need like ALU twice. Okay, let's split it into two states, right? That's the way how we can reason and think about it, and like when you're designing a new machine, right?
Right, and you would split it into multiple states by using the combination of multiplexers and flip-flops, kind of like we've been talking about.
Exactly.
Okay, so that makes a lot more sense now that I'm thinking about it. So the multiplexers and flip-flops just split it into separate states that we're working with.
Exactly. These are the things that enable us to like transition between a state. Would otherwise was not possible. Like
right, because in single cycle architecture we have that one single state at all times. Multi-cycle we have multiple states. Okay.
Exactly.
It feels like it would make more sense to call it single state and multi-state architecture then.
That's right. That's a good, maybe better word in that sense. Yeah.
And I think earlier when I was thinking through that example, I think I was thinking of pipelining instead. I looked a little bit ahead in the book because I was kind of wondering what the deal with the clock cycles were and why we had all the clocks in separate places. Right. And I thought about, why couldn't we just have all of these under one big clock and separate it? Right. And then I looked in the book and pipelining was there, and that's exactly what it was.
Yeah. That's it. That is necessary in pipelining. Yes.
So it looks like pipelining just makes a little bit more sense to me than the multi-cycle right now.
Right. Yes. And that's why it's predominant way of like doing microarchitecture, right? But clearly for teaching purposes, we prefer to separate this, right? So seeing this improvement,
right. So we would start with single cycle, which is usually the worst, the slowest. We go to multi-cycle, which has a lot of advantages, and then talk about pipelining, which kind of merges both and lets you separate everything out.
That's right. So clearly we can see like how these things evolve over time, right? Rather than one big bang that like we could not disentangle and like make a sense about design decision, right? Because that's important. We want to not only see we could start this course, but like discussing about the latest state of the art microarchitecture,
right?
But we get lost fast. We would never ever understand. Okay, like how, like was it like this Superman that designed this, microarchitecture like so elegantly now? that we couldn't do before. But seeing these precedents and the all design decision performance trade-off is necessary to understand things better.
Right. And I'm still getting used to, like, it's been a while since I've taken a class in computer science area. Because I'm an electrical engineering major. I'm also a senior. The last time I took a computer science class was 2.5 years ago.
Okay.
So I'm still trying to piece together bits and pieces as we go, that from things I've forgotten and trying to remember.
How it is different in electronic engineering? Do you have a separate computer architecture course, or
we actually, this is our computer architecture course. So we have to take, I think, 4 computer science classes.
Okay.
We have to take 145 and 146, which are like the introduction, and 146 is optional. You could take some mechanical engineering methods class or something. And then we have to take digital logic in this class.
Okay. So and you get a similar digital logic course, or the same?
It's the same digital logic course, because we basically take 4 of the computer science classes and take those. And that's what's really beneficial, is that a lot of electrical engineering people go on to get computer science minors.
Oh, okay. Yeah. That totally makes sense. Yeah, that's interesting. But I'm sure you have much more background on the electronic side and
right. So thinking of all these signals and digital signals and at the higher level is really weird for me.
Right. Yeah, like for us, computer science, like thinking about this lower level stuff is weird for us as well, right?
Right. It's approaching the same thing from different directions.
Yeah. And that's why, like, this computer architecture is useful to have a glance over all. I mean, like, good part of the stack, not all, obviously. Like for the whole, you need to like get a major in computer science and electronic engineering or hardware, right? In order to understand fully the whole, and also physics, right? To understand the electronic side, electron side, to understand the whole stack, but like limited time and not really necessary for most of us, right?
Right. Well, thank you for the lecture today.
Sure.
I know I learned a lot.
Thank you for discussion. Yeah, thank you. It was fun.